the three factors that determine how wide the interval is are, first, the standard deviation. Now, there's two kinds of standard deviation you can get. They are, and again, I'm using, as I'm talking about this, I'm contextualizing this discussion in doing an interval estimate specifically for means, not for standard deviations. So everything I'm talking about so far is for doing interval estimates of means. Okay, so the three factors that determine how wide the interval is are, the first factor is the standard deviation. And you can either get the standard deviation of the population if it's known. How might it be known? It could be past historical data has given it to us. Or if you're sampling from a population whose standard deviation is not known, then instead of using sigma, you'll end up using S. So let me talk about this. The bigger sigma or S is, the more variance there is in the population. So think about it. If there's a lot of variance in the population, will I need to have a smaller interval or a larger interval? Okay, think about it. I'm sampling from a population that has a lot of variance. If it has a lot of variance, is it likely that my point estimate is going to be close to the mean? Or is it less likely? If there's a lot of variance, it's less likely that my estimate is going to be very close to the mean. So what do? I extend my buffer zone, if you will. So the larger the standard deviation, the larger the buffer zone has to be, so that I can be confident that in my buffer, in my ballpark, is the actual population parameter. Okay, the actual population mean. So right down here in the blue, I wrote more variance in a population results in a larger interval requirement, so more width. Let me put that, more width. So there's a direct, I'll underline this, if you're familiar in algebra with direct and inverse relationships, there's a direct relationship between sigma and the width. Okay, let's look at the next thing. So that's one factor. The next factor is your sample size. If you take a large sample size, then you can be more confident about the results that you get from the sample. Doesn't that make sense? If I sample from my class, let's say I'm doing a class of 30 students and I'm trying to estimate the average grade in the class. Well, if I only sample 2 students, then how likely is that estimate going to be an accurate reflection on the whole class? I can't be that confident that sampling 2 students is enough to give me a good picture of 30 students, right? Because if I pick 2 students randomly, I could end up randomly getting 2 students who are doing very well, who are doing better than average, who are doing a little less well than average, or who are doing, I could end up with 2 students who are both doing poorly. So there's a lot of ways that estimate can get messed up. But the larger the sample is, the less likely it is that due to sampling error, my estimate will be way off what it actually should be. So there's an inverse relationship here. Okay, the larger the sample, let me get a pen, the larger the sample, the smaller the interval or width you need. Large, because you can be more confident about your estimation. So you don't have to add and subtract as much. The smaller the sample, the larger the interval you need. Okay, however, both of these things are not determined by U or I. Factors 1 and 2 are determined by the data and the population. I don't have any control over that. Okay, do I have any control over the standard deviation? Absolutely not. It is what it is. Do I have any control over the sample size? Not once I've chosen it. Once I take the sample size is set, correct? So those factors are determined normally in a problem. But how I can vary the width, and the factor I do have control over is this decision factor down here, and it's called the confidence level. anytime I do one of these estimates, I get to decide how confident I want to be about my estimate. Every time I do it, there is always going to be some uncertainty, but I can choose how much. So confidence level answers the question, how certain do you want to be concerning your estimate? What percent uncertainty, and that's alpha by the way, is acceptable to you? If you want to be more confident that your interval contains the actual mean, then you're going to need a larger interval. If you're content being a little less confident, you can go with a smaller interval. So if I said, if I wanted to be like 99% confident in my dog example, where's my pen? There it is. If I wanted to be 99% confident in my dog example that I'm capturing, maybe instead of going 4 out, I would go 10 out, 10 pounds in each direction. And I would say mean is between 28 pounds and 48 pounds. And maybe that would do it for me, that I would be 99% confident, confident of the estimate. And maybe this over here is only 80% confident. But you can never be 100% confident about an estimate because of sampling error, unless you sample the whole population, and then it's no longer a sample mean, is it? It's the actual mean. So you're not really doing a sample. It is what it is. So let me finish this up. This is a direct relationship, all right, the confidence level. You can see the more confident I want to be, the larger the interval I need. So anytime, here's my little summary, and this will finish it up for us. Anytime I do a sample, I will get the sample statistic. And we're saying that in this conversation I'm talking about sample mean. So I'll get X bar. But how far do I go in each direction? You see on the other page, I added 4 and I subtracted 4. Where there's a formula and it says how far I go in each direction is called the max error of my estimate. And it is equal to one of two formulas. You either have Z alpha over 2 times sigma over the square root of n. Or you have E equals T alpha over 2 times S over the square root of n. Sometimes you can use S in your Z if your sample size is large enough. Okay, anyways, so you have one of these two formulas that you use, and I'll explain on other videos which one you use when. Okay, that's not really what I want you to see here. I want you to see that if Z alpha over 2 is big, E gets bigger, right? It's a direct relationship because I'm multiplying here. The bigger Z is, the bigger this result is, and the bigger E is. The bigger my population standard deviation is, the bigger E is. But the bigger N is, notice I'm dividing by N, and when you divide by a bigger number, you end up with a smaller number. And look at what I said up here. Standard deviation is direct, confidence level is direct, but sample size is inverse. So you multiply. This piece right here depends on the confidence level. This piece up top depends. This is the piece that is related to your standard deviation. Both of these guys are direct, but this one is indirect, which is why we're dividing by it. So it's telling us what E is. Now I'm not telling you here yet how to calculate Z. All right, I will tell you in this video how to calculate alpha over 2, but I'm not going to go so far as doing the Z of alpha over 2. So, and let me just point out one other thing here. These parts are determined once you perform the experiment. This part you get to pick. Remember, Z alpha over 2 is related to your confidence level. Also, T alpha over 2 is related to your confidence level. So you get to choose those. You don't get to choose these. These are determined. Okay? Same thing down here. You pick this, These are determined by the data. So, what's your mean going to be? Your mean is going to be between x bar minus something and x bar plus something. And that something depends on whether you're using z or t. And it depends on this information that you put in. So last thing here is, how do you determine this alpha over 2?